Hey, you guys, this is Mrs. Duskevich, and I want to attack today one of our very favorite periodic trends, atomic radius. And actually, this is one of the most important of the periodic trends. So let's take a look at it and get right to it here. First off, we have the periodic law. And so it's nothing that you have to put under your pillow so you can remember anything. But just know that atoms with similar properties, they appear in groups or families of the periodic table. So if you recall, groups and families are actually columns, not rows. The rows are called the periods, the groups and families are called the columns. They are similar because they have the same number of valence electrons, or the most outer shell electrons, which also it helps tell how they're going to behave chemically. How are they going to bond? How are they going to donate or take electrons? How are they going to lose electrons and create some other things? So here we have the valence electrons, and just a quick recap. Do you remember how to tell the number of valence electrons for the elements in the S and the P block? So remember, the S block is here, and our P block is here. And if you just recall, we're just going to count and fill the octet rule more or less. So this first column, we have one valence electron, second column, two. Come over here to the third column, 3, 4, 5, 6, 7, and 8. Remember, we want the octet rule. Having 8 valence electrons is going to make the element very stable. How many valence electrons will the atoms in the D block and the F block have? So we also need to know this with transition metals. Sometimes even though we don't see them as valence electrons, sometimes they can behave as valence electrons. However, if you just look at the electron configuration, you are going to find that most of these transition and intertransition metals have 2 valence electrons because, for example, you're going to have 4s2, 3d10. So the 4 would be the outermost energy level with 2 electrons in it. Or you'd have 5s2, 4d10, and then the 5, energy level 5 would only have 2 electrons in it. Sometimes you'll only have 1 because sometimes you'll have that situation where a d orbital with higher energy will steal an electron out of your s orbital. So it'll just be 1 electron. And sometimes that does happen, and it's not uncommon. With these periodic trends, there are several important atomic characteristics that show these trends that we should know. And the first and most important is atomic radius, and it tells us basically the size of the atom. Now remember, radius is the distance from the center of a circle to the edge of the electron cloud. However, those electrons are moving so quickly, there's no way we could stop those electrons long enough to say, hey, wait a second, we just need to measure the distance from the nucleus to these electrons. So we do have another method to do this. And one method to do this is we use a covalent radius. So basically, covalent means that we take 2 elements or 2 atoms of the same element, and we're going to measure the distance in angstroms from one nuclei to the other nucleus. And then we'll just divide it by 2. So here's an example. These are bromine atoms, and they are 2.86 angstroms apart. So the radius of each angstrom then is 1.43. So we report the radius of bromine then as 1.43 angstroms. Just to get another idea, let's go back a slide really quick to get another idea of angstroms. Angstroms is also what we call picometers, and picometers is 1 times 10 to the negative 10 meters. So we're working with very, very small numbers and units here. Let's go back here. Okay, now the atomic radius, the trend. So the trend for the atomic radius in a vertical column is to go from smaller at the top to larger at the bottom of the family. So this really is pretty easy to kind of comprehend. And so basically, if you're looking at your periodic table, and here's just an outline of a basic periodic table. So basically what this says is, hey, as we go down the energy levels, 1, 2, 3, 4, 5, 6, 7, then we're basically filling another principal energy level each time we go down. So, therefore, of course, we're going to make a larger atomic radius. That makes pretty good sense. However, the part that is a little less obvious and is a little more difficult to grasp is the fact that as the atomic structures, we go from left to right, each step adds a proton and an electron. So what's happening here is we're adding electrons to existing principal energy levels or sublevels. So if we have our periodic table shape, and as we go across the periodic table, we're going to add more electrons and more neutrons and more protons and all that good stuff. So why on earth might we actually get smaller as we go across the periodic table? The effect is that the positive of the nucleus has a greater pull on the electron cloud. This is kind of what I think about sometimes is I like to use the analogy where if I'm hiking with my two children and I have my two boys and I'm hiking and I am mama nucleus and I'm just hanging out and I have two kids to watch and our rule is you can't get out of my line of vision. I have to be able to see you. So therefore, it's easier for me to see and just hang on to two children than it is to hang on to eight children, for example, if they brought three of their friends each. So it would be, I would have more of a pull on two because it's just me as one person than I would have a pull on eight. So what we have to think about here is the more positive the nucleus, so the more protons there are in the nucleus, because remember, protons is what makes a nucleus positive. Therefore, we have a greater pull on the electron cloud. There's more protons in that nucleus, like more mama is watching out for those electrons. So the nucleus then being more positive, the electron cloud is more negative. However, remember those electrons are very small, so there's more of a pull with those protons because there's more mass. So this increased attraction basically pulls the cloud in, therefore making the atom smaller as we move from left to right across the period. And that basically is referring to its effective nuclear charge. And this is where I always have a lot of students ask me this question. Okay, MSD, those electrons are moving so fast. What keeps them into place? Well, what keeps them into place is this pull that the electron feels from the positive nucleus. Remember, the nucleus is positive here. So it's this pull, but yet that nucleus can't just pull in all those electrons super duper easily because those electrons are moving so fast that there is some distance between the two. But this effective nuclear charge, and sometimes we refer to this even as ENC, the effective nuclear charge is that pull. It's not a force, it's more like, again, an attraction. So the closer the electron is to the nucleus, the more pull it feels. So if you have like a 1s electron, it's going to feel more pull than a 7s electron, for example. So as effective nuclear charge increases, the electron cloud is pulled in tighter. So even if we think about, say we think about, uh, let's see, sodium. Sodium has 11 protons and 11 electrons. Whereas if you go across on the periodic table, you're going to have argon, and argon has 18 protons and 18 electrons. Argon is actually going to be smaller, even though it has 18 protons and 18 electrons. The reason is because those 18 protons have a higher effective nuclear charge than those 11 protons from the sodium. Therefore, those 18 protons from argon are pulling the argon atom or pulling those electrons in tighter. So the overall trend in atomic radius looks like this. And I know it looks a little crazy, but you'll notice as we get down toward the bottom left of the periodic table, and this one's not really represented because francium has such a tiny half-life, it's very hard to actually to measure of any sort. But as we get close to this portion of the periodic table, notice how much larger the actual atomic radii are than, for example, helium. So one way I like to remember, and it's not the nicest, but it helps a lot, is we're going toward francium. And although francium has a very short half-life to measure this, but I like to think of it as fat franny. It just helps me to remember, okay, which is the largest atom potentially on the periodic table, and that would be francium. Francium has electrons in 7 energy levels, and it only has 1 valence electron in comparison to others beyond it. So therefore, that 1 valence electron is being pulled in, but it's not being held super duper tight. On your help sheet, it'll be helpful to draw arrows like this going toward our good old francium 7s1. So as we get closer to the bottom left-hand corner of the periodic table, our atoms get much larger. Therefore, the helium are much smaller. And again, they're much smaller because they're being held tightly to the nucleus, and there's not a high effective nuclear charge because there's only 2 protons in a helium. The final thing here is shielding, and something else we need to think about as to how tightly those electrons are held. So as we add more principal energy levels, so principal energy levels are, again, like 1 through 7 on your periodic table, going through like 1s, 2s, 3s, and so forth. As there's more principal energy levels added to these atoms, the inner layers of the electron shield the outer layers from the nucleus. So let's say I have something, an atom with electrons in the 7s. Well, these in here are shielding from the nucleus. Say I have the nucleus. These are shielding from the 7s electron. This 7s electron is very far from the nucleus. So therefore, the effective nuclear charge on the outer electrons is less. So those outer electrons are actually less tightly held. It's just like, let's say I was in a classroom and here's Mrs. D and here's Naughty Kid by the door. And Mrs. D can't get to Naughty Kid because there's so many nice kids in between Naughty Kid and Mrs. D. So therefore, these nice kids are shielding the naughty one from Mrs. D. So it's, again, less tightly held, so they'll probably be naughtier. So anyway, hopefully that can help, and we'll get more toward periodic trends. But atomic radius is the #1 most important periodic trend because it leads to so many other things when we get to bonding. Hang in there, guys. You're doing